Okay, welcome to lesson 3, displaying data. Okay, so in the last lesson, just as a recap, we talked about populations and samples. In the next few lessons, we're going to start dealing with samples of data. And the first thing we have to talk about is displaying and graphing data. So there are a lot of different types of graphs. You can have bar graphs, you can have pie charts. Those are graphs that you're probably used to seeing. I'm going to focus this lesson on numerical graphs of numerical data, because when you're doing data analysis, the first thing you want to be able to do is get a feel for the shape of your data. In other words, is the data pretty evenly distributed? Do you have a lot of high values and very few low values? Do you have a lot of average values and very few high values and very few low values? And when I say the shape of a distribution or the shape of your data, we're going to see by the end of the lesson what I mean by that when we start looking at histograms. So first I need to talk about frequency distributions, because this is kind of at the heart of not only graphing, but a lot of data analysis that you do. So we're going to start with something called a frequency distribution. Again, we're going to talk about shape of data in lesson 5, but we want to have an idea of just how the data is distributed. So let's start with a sample of 50 households, and we're going to ask or determine how many cars that household has. So here we see a list, a sample of 50 households. And so the first couple have 1 car each, the third one has 2 cars, 4 cars, 2 cars, and so on. Okay, so it doesn't look like much when we just look at it. I mean, we want to be able to do some analysis on these numbers, but first we have to display them visually in a way that makes sense. So step 2 is we're going to make a frequency distribution table. And that's what we have in the table below. When we talk about a data distribution or frequency distribution, what we're basically talking about is a list of all possible values of X. You remember in the last lesson I talked about discrete versus continuous data? And I mentioned that discrete data, you can list all possible values. So we'll get to the continuous data later. Right now, we are figuring that how many cars a household has, that's discrete data. I mean, how many different values for, almost all households are going to have 5 or fewer. We have a 6 in this data set, but bottom line is you can fairly easily list all the possible values. You can't have, 2.5 cars. It has to be a whole number from 0 to 6. And the second column, so that's the first column here. The second column just lists the frequency. How many households have 0 cars? Well, there's three households have 0 cars, 13 that have 1, 15 that have 2. And we could do this just by taking our list here, and you could do the whole counting thing. We have 1, 1, 1, 3, 1. Then you have 1, 2, 1, 2, 0, and so on. I'm not going to go through the entire process here, but that's really what we're seeing in column 2 of this table. Now, the third column is what we call relative frequency. So relative frequency, what we're doing here is we're taking the frequency and divide that by the sample size. The sample size in this case is 50, so 3 out of the 50, or 0.06. In other words, 6% of the households have 0 cars, 26% of the households have 1 car, and so on. The relative frequencies have to add up to 1. When we get to probabilities, we'll get into the relationship between decimal and percent, but basically 0.06 equals 6%. And the 1 equals 100%. We express percents as decimals. We have to do that, especially when you look at some of the formulas we'll see later on. Probability is generally expressed as a decimal or fraction, and relative frequency is also. So the point of having relative frequency is that you can easily convert all of these numbers into percentages simply by moving the decimal 2 places to the right. So that's the idea of a frequency distribution table. Now, what do we do once we have this data, once we have the table? Well, the next step is to build something called a histogram. Now, you've seen bar graphs before, where you have some variable, maybe it's, I don't know, favorite color, and of course the higher the bar, the more popular that color is. So this is what we know as a bar graph. Now the bar graph, notice I selected qualitative or categorical data for this. In other words, non-numeric. Blue, red, green, and orange. They're colors. I can't do any math with them. A histogram is a specialized version of a bar graph. Now, in the bar graph, we construct rectangles to show the height, to show the frequency. So there might be 3 blue, 2 red, I really draw this to scale, 5 green, and so on. So a histogram follows those same rules. But a histogram is a special type of bar graph, and there are some specific rules. Bar graph, the rules are kind of loose. You put all the possibilities on the x-axis, you put all the heights on the y-axis, and so on. There's not a whole lot of rules that go into it. So the width of each rectangle is the same. That may seem rather intuitive. Why would you put different widths? I mean, if you look at the bar graph, if I suddenly made the orange bar twice as wide, it would look kind of awkward, but it doesn't really change the meaning of the graph, because the colors are not in any particular order. So while it might look weird to make one of the bars very wide, it doesn't really change the meaning of the graph at all. That is not the case for a histogram, because in a histogram, we're dealing with numeric data, and so the numbers are going to be in a particular order. And if you make one bar wider than another, if you take, let's say, the car's data, if I make, well, the numbers are not spaced. If you want to account, if you're going to account for the number of high and low data points, you don't want to give the impression that the 4s are further out than they actually are. That's a very important characteristic of the histogram. Each bar represents either a single value if it's discrete data, or an interval of values if it's continuous data. We'll get to the continuous data in a bit. Properties specific to histograms. Each data point or interval is represented by a single bar. We saw that. The bar widths are equally sized. If the bar represents an interval of data, in other words, if you have continuous data where a bar represents an interval, each bar must represent the same interval of data. So if the first bar represents numbers 0 through 10, or 1 through 10, the second bar has to represent 11 through 20. Each data point must fit exactly one class. I'm going to discuss this in more detail when we get to continuous data. Every data point between the lowest and highest value must be represented both in the frequency table and in the histogram. So I'm going to come back to these definitions. If you're not quite clear on that third bullet point yet, that's okay. Once we get into continuous data later on in the lesson, I'm going to come back to this definition. So for now, let's just see a histogram from the car's data and just kind of see what that looks like. Now, I used a website called StatCrunch to build the histogram. But if we go back to the original data, you could just kind of recreate it down here. Just copy down the frequency distribution from above. And basically you can see that as in a regular bar graph, on the height of the bar on the y-axis is represented by the frequency of the data. And so when we look at this, we can see that we have data that's a little bit right skewed. And when I say right skewed, I mean that there are more outliers or more low data points on the right than there are on the left. We'll get more into that later, into skewness later on. Now, the cars data, and I don't really like the way they display it here. I can't get StatCrunch to put, really, numbers should go in the middle of the bar. Generally, when you're dealing with discrete data, you want to make it clear what value each bar represents. Of course, all the bars are equal width, and something I don't think I touched on earlier is that notice all the bars are touching. In the bar graph, you can kind of play fast and loose with the spacing and the width, but it's very important that there are no gaps, that all the bars are up against each other is a very important reason for that. Why do the bars have to touch? Well, at the very least, they have to be equal intervals. So let's suppose they didn't touch. I mean, this is not something you would see in a typical bar graph anyway. I'm just going to kind of make up data here. I just want to illustrate what happens when the bars don't touch. Oh, and by the way, one other thing I have to talk about here is every possible value of x. I did get into this above, but it was for the continuous data. I'll just rewrite it down here. Must be represented on the graph, even if has a zero frequency. In other words, I think we had one that was 6. So suppose we added another data point to this distribution where there was a household with 8 cars. I can't put the 8 over here. We're going up by ones, therefore I have to continue going up by ones, and I have to put the 8 in there. And so that 7 needs to be represented both in the frequency distribution and on the histogram. That's very important. And the reason is, actually, let's say that last data point is not an 8, but suppose it's a 10. I can't imagine too many households have 10 cars, but just for the purposes of illustration. 10 is a very unusually high number. It's something that we refer to as an outlier. It's very different from the rest of the data points. This is why the bars have to touch. This is why you have to have equal intervals. And this is why even if there are no households with 7, 8, or 9 cars, they must be included both in the frequency distribution and on the graph. Because if I were to just, in the alternative, if I were to just take the 10 and scrunch it up against here, if 10 is an unusually high data point, that needs to be reflected in the graph, where there's empty space here. And so you want to have an even scale all the way across. You don't want to make that last data point look more homogeneous than it really is. And so I need to say, wow, we're all the way out here because 10 is a very high, as an unusually high data point. And if I put it right up against the 6, that's not gonna be expressed as much. I need to really show that that's an unusually high data point. And that's the same reason why the bars have to be equal width and they have to touch, just so you have that even scaling all the way across. And so that's really what the information that a histogram tells you. I can see where the highest number of data points are. Sometimes we'll take a smooth curve and draw it over the histogram. And so I can kind of see the pattern here. Most, or the plurality of households have 2 cars, slightly fewer have 1, and it really drops off after 3. Very few 4, very few 5, and this sample anyway, there are none after 6. Now, I'm going to go to another example here because the last example was an example dealing with discrete data. Now, this data, suppose we have another example here. We have 50, it's still a sample of 50, but it's 50 students taking a math test and have the following scores. All right. Now, we want to make a frequency distribution and a histogram for this data too, but we're going to have to do this a little differently. And I mentioned in the last lesson that continuous data means one of 2 things. It means that either x, and again, x is going to equal the score on a math test. And this is why we refer to it as a random variable. This first student had a 90. That 90 didn't come from some formula. It came from grading the test and totaling up the score. So this value of x had no value until, grading the test wasn't really an experiment, but the bottom line is the 90 came from an experiment or survey or measurement in some case. It didn't come from a formula. But in any event, continuous data means that x can have an infinite number of possible values, or at the very least, a very large possible number of values. Now, we can say, okay, well, you only have 101 possible scores, 0 to 100. It's 1 to 100 plus the 0, so it's 101 possibilities. So it's not infinite, but it is very large. And I want to go back to the last example for a moment, and the example of 10 cars. Now, suppose that you have a car collector in this data set that has 55 cars. Well, that's a little unusual, and I think there are ways to still express this data in terms of discrete data, but if you had a collector with 50 cars, I'm just going to take a guess where 50 would be on here, 20, 30, 40, 50. Yeah, it would have to be, that car collector would have to be all the way out here. In other words, everything, I'd have to have an 11 and a 12 and a 13 and a 14. I would have to include every single number between 0 and 50. Every possible value for x. Basically, everything between the minimum and the maximum data point. Now, if you have even 50, or in this case, 51 possible values of x, you can see that would be a problem. In other words, even someone with 10 cars, I have to extend the table all the way out and put zeros, because every possible value of x has to be accounted for. Meaning that if households range from 0 to 10 cars, I have to have 11 rows in my table. Okay, with that thought in mind, you might see why we have to treat the test data, the math test data, as continuous. Because if I treat this data as discrete, and I want to build a table, a frequency table from this data, well, you guessed it, I have to have a 0 row and a 1 row and a 2 row and a 3 row and a 4 row. In other words, I have to, every value from 0 to 100 has to appear in this table. That's going to be a pretty long table. What's worse is, not only do I have to have every number on the x-axis going all the way up to 100 But since very few of those numbers appear more than once, in other words, there are very few duplicates. There's probably a few. Yeah, 75 is in there a couple times, but not that many duplicates. Meaning that a lot of these bars, there's going to be large gaps in here, and a lot of bars are just going to be one high. This doesn't tell me anything. So what's the remedy to this? Well, I kind of hinted at that earlier. And I said every value between 48 and 100 is actually 0. There's a 0 on the test in there. But even 48 to 100, that would still be not very practical. So what we're going to do is we're going to group the data into classes. So let me just go ahead and show you what that looks like. So I still have to include every data point, but I'm going to group them into bins of 10. So 0 to 10, 10 to 20. Oh, by the way, let me just talk about the notation here. This notation, that means at least 0 and less than 10. So since we're dealing with all integers, it basically means 0 to 9, 10 to 19, 20 to 29, 30 to 39, and so on. So there was one data point in the 0 to 10 range, none in the 10 to 20, 1 in the 20 to 30, 0 in the 30 to 40. And again, you can see how this matches up. So we're grouping them by tens. That way, we only have to have 10 rows instead of 101. So the rules otherwise are the same as for the discrete data. The only difference is because we have so many different possible values of x, we're going to make things a little easier, not only easier, but make the graph more meaningful by grouping them into tens. The same rule before for the relative frequency. Again, since there are 50 data points, the relative frequency, this is 1 divided by 50. 0 divided by 50 is obviously 0. This is also 1 over 50. 5 over 50 is going to come to 0.10. So you just put that in a calculator, and that's the same as saying 10% of the data is in this interval. Now, I want to go over just a few comments here. Now, I said earlier, I'm going to go back to the rules of histograms. Now, some of this didn't make sense earlier, so let me just kind of repeat it now. Each bar must represent the same class width. So in other words, if I decide that every class is going to represent 10 possible values of x, if I decide if one represents a class width of 10 different values, the next one has to represent 10 values. In other words, a counterexample is I can't say, well, the first row is going to be 0 to 10, and the second row is going to be 10 to 30. Right? This encompasses 10 possible values. This encompasses 20 possible values. I can't do that. So that's what this point means here. Every data point must fit exactly one class. In other words, there can't be any ambiguity. As soon as you see a data point, every data point must fit one class and only one class. And that's why I was very specific about the greater than or equal to. I'll go back to the table and show you that. Every possible data point between the lowest and highest value must be represented. Again, this is what I was talking to you earlier about no gap. Okay, so this is what I mean by equal class width. Each row has an interval class width of exactly 10. Now, there's no rule saying it has to be 10. I simply chose 10 just because it's convenient. Therefore, that way you only have to look at the first digit of a number to tell which class it goes into. We could have made this a class width of 8. There's no hard and fast rule in terms of your class width. And if it turned out that the lowest data point was 22, do I start the first class at 20 or do I start the first class at 22? That's actually up to you. So there is some flexibility, but just a rule of thumb, because, and this is not scientific in any way, but probably 5 to 20 intervals or 5 to 20 classes. That's a pretty big range. It's more of an art than a science. If you have too few intervals, you're going to have a lot of, the data is going to look more homogeneous than it is. You're going to have a lot of, you're not going to have a whole lot of columns, and there's not a whole lot of possibilities. If you have too many intervals, it's kind of like the discrete data. You're going to have a lot of zeros and ones. So if you have too few, your data could end up with very few classes like this histogram like this, because so many data points are packed into each bar that you're only going to have 2 bars, and it doesn't tell you anything. If you have too many classes, too many intervals, well, what you'll end up with, you have a lot of gaps and a lot of zeros and ones. That doesn't tell you anything either. 5 to 20 intervals, that's generally a rule of thumb. I just went by intervals of 10 just because it was convenient. I also want to emphasize the idea of every data point fitting into exactly one interval. And that's why I was very careful the way I set these intervals up. If I just said, so why can't I just make this 0 to 10 and 10 to 20? Well, the problem with that is if you have a data point that's exactly 10, it's ambiguous as to which one of these classes it goes into. I can't have any doubt. So looking at this, if I have something that's exactly 10, it clearly goes in this class. Because this is less than 10, this one is at least 10. There's no issue with where it goes in. Now, another thing is the way I have these classes set up, we knew that in our data set there were no decimals, that we were dealing only with whole numbers. And so the question is, could we have made our data set like this? Could I have set it up like 0 to 9, 10 to 19, 20 to 29? Could I have set the rows up like this? And the answer is yes. But there's a caveat to that. Because luckily enough, we don't have any decimals in our data set. A setup like this would work for this particular data set, but then you have to ask yourself, if we had decimal data, where does a 9.5 go? It can't go here because we're only up to 9. It can't go here because we start at 10. You see the problem? So even though we don't have decimal data here, if I have a 9.5, a 9.5 would definitely go in here because it's less than 10. So this goes everything up to but not including 10 and starting at 10. Therefore, every real number, decimal fraction included, is accounted for in this table. It's not necessary for this particular data set, but it's a good habit to get into. Okay, so let's finish up by taking a look at the histogram. Now, this time it actually is appropriate to put numbers on the borders. That way you can tell this bar represents 0 to 10. This would represent 10 to 20. And again, this is very important. There's no data in the 10 to 20 range, but we have to put the gap there. We have to list them on the axis anyway. This one represents 20 to 30, 30 to 40. There aren't any, and so on. And again, we see the shape of this data. And when I say shape, I mean there are outliers. There are unusual values at the bottom, but toward the top, the data is a lot more clustered. And what you would hope for in exam grades, you would hope for most of them to be 70 and up, or at least 60 and up. Okay, so that brings us to the end of lesson 3. In the next lesson, we're going to start the next module, descriptive data, descriptive statistics, and we're going to start doing the calculations, finding the mean, median, mode, and all those other nice things of how to describe data.